All right, today we're diving into a real chemical mystery. It's a tale of a single compound with a complete split personality. On one side, you've got hydrogen chloride gas, and on the other, you have the super corrosive hydrochloric acid. Now get this, they have the exact same formula, HCl, but how they act, totally different worlds. And that leads us to the big question for today. How on earth can one simple molecule live this kind of double life? How can it be a pretty harmless gas one minute and a seriously powerful, dangerous acid the next? Okay, let's play detective and crack this case. So our investigation has to start where all chemistry stories do, right? Deep inside the molecule itself. You see, the very first clue to understanding HCl's dual nature is hiding in the bond that holds it all together. Okay, so picture this. Inside every single HCl molecule, there's this constant tug of war going on over electrons. Chlorine, you see, is way more electronegative than hydrogen. That just means it pulls the electrons they're supposed to be sharing much, much closer to its side. Now, it's not strong enough to rip the electron away completely, but it does create this little imbalance, a slight negative charge on the chlorine end and a slight positive charge on the hydrogen end. This is called a polar covalent bond, and this polarity, this is the secret that's about to unlock everything. So let's meet the first of our two personalities, hydrogen chloride in its pure, dry, gassy state. This is HCl when it's just minding its own business, with no accomplices around to get it into trouble. So how do you actually get this gas by itself in a lab? Well, it's a pretty classic setup. You take regular old table salt, that's sodium chloride, and you react it with some concentrated sulfuric acid. Heat it up gently, and poof, out comes pure hydrogen chloride gas, which you then have to dry and collect. But in chemistry, the little details are everything. You have to keep the temperature below 200 degrees Celsius, because if you go hotter, you form this hard, glassy crust in your flask that's a nightmare to clean up. Then you have to dry the gas, and you can only use concentrated sulfuric acid. Why? Because other common drying agents will actually react with the HCl. And finally, since the gas is about 1.3 times heavier than air, you collect it by letting it sink and push all the lighter air up and out of the jar. And here is the crucial piece of evidence for its innocent identity. This dry gas, it's colorless, smells pretty pungent, and yeah, it's heavier than air. But as a covalent compound, it doesn't have any free-moving ions, and that means it won't conduct electricity, and this is the big one, it shows zero acidic properties. You can stick a piece of dry blue litmus paper in there all day long. It'll stay blue. The definitive test? The real giveaway? Bring a glass rod with some ammonia on it nearby, and you get these thick, white fumes of ammonium chloride. That's the signature calling card of HCl gas. Okay, so if the dry gas is non-acidic, if it's relatively harmless, there has to be a trigger, right? Something has to happen to cause this wild transformation into its other, much scarier personality. Let's just pause on that for a second. By itself, as a gas, HCl is a covalent compound. The hydrogen and the chlorine atoms are locked up tight together. It's not an acid. So this is the real turning point in our little mystery. If HCl isn't the culprit on its own, then it's gotta have an accomplice. So what's the key? What is it that unlocks all of that hidden acidic power? And the accomplice is water. That's it. It's just water. So here's the critical moment. When that polar HCl molecule dissolves in water, which is also a polar molecule, by the way, the water molecules basically gang up on it and just pull it apart. This whole process is called ionization. The HCl molecule splits into a negative chloride ion, and that lonely hydrogen ion immediately latches onto a water molecule, forming something called the hydronium ion, or H3O+. That thing right there, that is the true source of acidity. No water, no ionization, no acid. It's that simple. So the transformation is complete. Our Jekyll and Hyde molecule, HCl gas, has now become hydrochloric acid. So let's check out the evidence of its powerful new identity. I want to start with just a number, 452. What in the world could that be? Get this. That's the number of volumes of HCl gas that can dissolve in just one single volume of water. That is an absolutely insane level of solubility. And there's this incredible demonstration that shows this perfectly. It's called the fountain experiment. You set up a flask full of dry HCl gas, and you introduce just a few drops of water. Well, the gas dissolves so ridiculously fast that it creates a partial vacuum inside. The higher air pressure on the outside then forces water from a beaker below, water that has blue litmus in it, up a tube, creating this spectacular red fountain inside the flask. It's beautiful, and it's a perfect 2-for-1 proof. The fountain itself shows that crazy solubility, and the color change from blue to red proves its new identity as a powerful acid. And now that it's a true blue acid, it acts like one. It does all the classic acid things. It'll react with active metals like magnesium and bubble off hydrogen gas. It'll neutralize bases like copper oxide to make salt and water. And of course, it'll react with carbonates and give you that telltale fizz of carbon dioxide. The whole shebang. But its power doesn't even stop there. If you persuade it a little bit, you can actually use its strength to release the chlorine that's locked up inside. If you heat concentrated hydrochloric acid with a strong oxidizing agent, like manganese dioxide, you can force the HCl to give up its electrons, releasing pure, pungent greenish-yellow chlorine gas. And now, for the ultimate demonstration of power, think about gold. Gold is a noble metal, right? It's famous for not reacting with anything. And it's true, neither hydrochloric acid nor nitric acid can touch it on their own. But if you mix them together in a very specific 3-to-1 ratio, you create something new, something almost legendary. Aqua regia, or royal water. This mixture is so powerful it can do the impossible. It can actually dissolve gold. So there we have it. We've seen both faces of HCl. We've examined the evidence, we've identified the accomplice, and we totally understand the transformation. I think it's time to say, case closed. This final side-by-side comparison really just tells the whole story, doesn't it? As a gas, HCl is a covalent molecule. It's not acidic. It's a terrible conductor, and you identify it with ammonia. But dissolve it in water, and bam, it becomes a collection of ions. It's strongly acidic, an excellent conductor, and you'd use silver nitrate to find it. They're like two completely different chemical entities, and water is the only difference. And look, this isn't just some weird fact for a chemistry class. This dual nature is hugely important. Hydrochloric acid is a workhorse in industry, cleaning steel and all sorts of things. It's a basic tool in every lab. And maybe most amazing of all, it's the acid inside our own stomachs, breaking down our food and killing off nasty bacteria. Understanding these two personalities is really key to using its power safely and effectively. So after all that, what are the key takeaways from this case? Well, first, water is everything. It's the catalyst, the accomplice that enables ionization and turns a gas into a strong acid. Second, that fountain experiment is just the most dramatic and coolest visual proof of both its solubility and its acidity. And finally, aqua regia, that just shows its ultimate power, the ability to dissolve gold itself. The case is closed. HCl's identity isn't fixed at all. It's completely defined by its environment. So that leaves me wondering, what other simple molecules out there are hiding a similar kind of double life?